Welcome to AI Paper Slop. Today we were jumping straight into a paper called Native Video Action Pre-Training for Generalizable Robot Control.
Yeah, this is the one introducing Lingbot VA 2.0 from Ant Group.
Exactly. And the core argument here is basically a massive challenge to current embodied AI research. They're arguing that repurposing off-the-shelf generative video models, like generic VAEs and bidirectional diffusion models, is just a fundamental dead end for robotics.
Right, which is a big claim. But instead, they built a native video action foundation model completely from the ground up.
And it relies on four main pillars. First, you have a semantic visual action tokenizer that actually extracts latent actions from completely unlabeled video.
Which is huge for data scarcity.
Totally. Second is a causal pre-training paradigm trained from scratch. Third, they use a sparse mixture-of-experts DIT backbone. So it scales up to 13 billion parameters, but, and this is key, it only keeps 1.9 billion active for fast inference.
Yeah, the efficiency there is wild.
And fourth, they have this Foresight Reasoning for real-time, closed-loop asynchronous control that peaks at like 225 hertz.
So, okay, let's unpack this, because if you are an ML engineer building physical robots right now, you have probably run into the exact wall this paper is describing.
Oh, absolutely. Everyone is hitting this bottleneck. And to understand why Lingbot VA 2.0 just abandons those repurposed models, you have to look at what generic video models are actually built to do.
Right, like standard variational autoencoders.
Exactly. Standard VAEs, which are in pretty much all the popular video generators, are optimized strictly for pixel reconstruction and compression.
Just pushing pixels around?
Yeah. I mean, when a VAE looks at a video of a robot arm pushing a block, its loss function only cares about reconstructing the RGB values, the silver arm, the red block.
It is no concept of physics.
None.
Yeah.
It doesn't build a representation of mass or spatial geometry. It just knows how to recreate a specific cluster of red pixels.
I like to think of it as asking a really, really talented painter to copy a photograph pixel by pixel.
That is a great analogy. Right. Because they can perfectly reproduce the image on the canvas. It looks flawless. But if you ask that painter, hey, how heavy is that object you just painted? Or how would it fall if I pushed it? They have absolutely zero idea.
Yeah, the visual fidelity is totally decoupled from physical reality. And what's fascinating here is the structural mismatch between bidirectional pre-training and causal deployment.
The temporal issue.
Exactly. If you look at how a generic video backbone is trained on web data, it leans heavily on bidirectional attention. The model can see the entire video file at once.
So to denoise frame 10, it's looking backward and forward.
Right. It looks at frame 5, but it also looks ahead at frame 15. It relies on the future to figure out the present.
But then you put that on a physical robot, and reality enforces strict causality. The future frames literally do not exist yet. You can only act based on the past.
And the standard industry workaround for this is just slapping a causal mask on these pre-trained models during fine-tuning. But the paper calls out that this brute force retrofitting just causes massive catastrophic forgetting.
Because you're blinding it to the future it learned to rely on.
Exactly. You break the attention weights. So all those broad, general physical priors the model learned from terabytes of web data, they just erode away. You're forcing a structure that contradicts its own architecture.
Not to mention the latency. I mean, iterative denoising of high-dimensional video tokens takes a ton of math.
Oh, it is incredibly slow.
Right. If your system needs to run a 50-step diffusion process just to move a motor 1 millimeter, you create a serial bottleneck. The robot literally stutters waiting for the compute.
Which you obviously can't have in a real dynamic environment.
So, knowing all this, the authors just throw out the old tokenizer entirely. That is their first major shift. Instead of a pixel-centric space, they build a shared semantic latent space.
Yeah, they completely decouple the visual tokenization from simple pixel reconstruction. First, they align their visual latents with a frozen foundation model. Specifically, a really robust perception encoder.
And they use temporal average pooling across the frames for that, right?
Right. That forces the latents to capture high-level semantics. The pooling collapses the dimensions just a bit, so the model learns the actual meaning of the scene.
But it still keeps enough per-frame detail to track the physical states.
Exactly.
Well, I really want to focus on their latent action tokenization phase because this seems like the answer to the huge data scarcity problem in robotics. They are using labeled robot data for this.
No, not at all.
They just use random unlabeled web video, and they run an inverse dynamics model, an IDM, and a forward dynamics model, an FDM, on consecutive latents.
The mechanics here are brilliant. So say you have a web video of a person opening a drawer. Frame A, the drawer is closed. Frame B, the drawer is open. The IDM takes both frames and predicts a transformation between them.
But there's a massive bottleneck on that transformation, right?
Yes. That transformation is squeezed into a very compact latent variable. If it wasn't tiny, the network would just pass all the static pixel data through and learn absolutely nothing.
So the bottleneck forces it to ignore the background and isolate just the delta, the actual action of the drawer opening.
Right. And then the forward dynamics model, the FDM, takes that compact action variable, combines it with frame A, and tries to reconstruct frame B.
And it outputs a transport map and a residual to do that.
Exactly. The transport map calculates how the stuff in frame A needs to physically move to match frame B. And the residual fills in any new information that gets revealed, like what's actually inside the drawer.
Okay, but I have to push back here. If this pipeline is trained on random human videos, someone opening a drawer, a dog catching a frisbee, how does that translate into actual control data for a robot?
I know, it sounds counterintuitive.
Right. The model has no idea what the specific joint angles of the robot are or what torque to apply.
And that is the beauty of latent actions. They map world states and inferred actions into the exact same semantic space before they even worry about the hardware specifics.
So it's learning the structure of physics first.
Exactly. By running this loop across massive amounts of web video, it learns universal geometry. It learns objects have boundaries, that they block each other, that force changes a trajectory. It's building a physics engine in latent space.
Wow, so then when you finally give it a tiny bit of actual robot demonstration data, it isn't starting from scratch.
Right. It already knows how a drawer opens. It just has to learn the specific mapping between that universal latent action and its own local motor commands.
Okay, so the tokenizer builds this perfect semantic map of the world. But obviously, a map is useless if the engine processing it is too slow to drive the hardware.
Which is why they abandon the fine-tuning approach completely. Instead of retrofitting, they train a causal diffusion transformer, a DIT, from scratch.
Strictly on web scale data.
Yes, and strictly with a causal mask from the very first gradient update. So it perfectly matches the flow of reality. No architectural shock when you finally deploy it.
And to get massive capacity without tanking their inference speed, they use a Mixture-of-Experts video stream. They follow the DeepSeek mode principle.
Yeah, the specs on this are impressive. It uses 128 routed SWIGLU experts with top 8 routing.
So it's roughly a 13 billion parameter model, but for any given token during inference, only 1.9 billion parameters are active.
Which gives them a huge asymmetric scaling advantage. The video stream handles the insane complexity of the visual world using the sparse MOE. Meanwhile, the action expert, which handles the low-dimensional motor commands, stays fully dense and active.
It's kind of like hiring a massive 128-person consulting firm. You have all this hyper-specialized expertise in the building, but for any specific problem, you only activate and pay for the 8 exact experts you need.
That's a perfect way to look at it.
You get the brain power of a 13 billion parameter conglomerate, but on a 1.9 billion parameter startup budget. No compute tax on every single pass.
But, managing that firm is tricky. You run into the issue of router collapse. The router network can get lazy and just decide 3 specific experts are good enough for everything, leaving the other 125 completely idle.
Normally, you'd fix that by adding a load balancing penalty right into the loss function, right?
Yeah.
Mathematically punishing the model if it doesn't distribute tokens evenly.
You could, but doing that pollutes the primary diffusion flow matching objective. The gradients get incredibly messy because it's trying to learn complex physics and balance its own router at the same time.
So Lingbot VA 2.0 uses a loss-free balancing strategy instead.
Yeah, they use aux-free bias updates. So outside the main gradient calculation, they dynamically adjust a correction bias on a routing logits.
So if an expert is getting too many tokens, it just lowers its selection bias. If one is starving, it raises it.
Exactly. It forces utilization across all 128 experts purely at the routing layer. The diffusion gradients stay perfectly clean.
That is incredibly elegant. But even with this fast, balanced engine, they found a major failure mode if the training objective isn't set up right. Because if a model runs at a high frame rate and only predicts the next single frame, it just becomes lazy.
Right, because at high control frequencies, frame T and frame T+1 look almost identical.
Barely any difference.
Yeah. So if your loss function only checks that one next step, the easiest path for the optimizer is just to learn the identity function. It just copies the previous frame. The loss drops, but it hasn't learned any physics.
It just acts like a static camera. And we see this a lot where Short-term visual continuity overrides actual trajectory dynamics. The model knows what the object looks like, but completely forgets where it was moving.
Exactly. So to fix this myopia, they implement multi-chunk prediction, or MCP. They attach these lightweight prediction heads to the main DIT backbone to predict 1, 2, and 3 chunks into the future all at once.
Giving it dense temporal supervision.
Yeah, and if we connect this to the bigger picture, this is profound for representation learning. If the network has to predict the scene 3 chunks ahead, it cannot just copy the current frame.
It mathematically has to encode velocity and momentum into the hidden state.
Right. It forces the latent space to actually understand physical intent and trajectory.
And this MCP acts as a massive accelerant. The paper says they got a 2.3x training speedup. It hits the baseline's 45,000 step accuracy in only 20,000 steps.
Which is a huge efficiency gain.
But the training story also includes their multitask co-training recipe, because they explicitly avoid training in sequential stages.
Right, because sequential training where you do text to image, then text to video, then finally fine-tune on a tiny bit of robot data, that is exactly what causes the catastrophic forgetting.
The distribution narrows too violently.
Exactly. The weights just overwrite all the broad world knowledge it learned initially.
So Lingbot VA 2.0 just optimizes everything jointly from day one. Text to image, text to video, video action, in-context learning, and human-robot co-training all feed into the Causal DIT at the same time.
The only thing they tweak is the mixing weights of the data batches. So the model stays grounded in general visual reality, even while learning specific physical manipulations.
Okay, so we have a hyper-optimized, physically grounded model that hasn't forgotten its priors, but deploying a smart model in the cloud is wildly different from deploying it to a chaotic physical robot.
Oh, absolutely. Model latency translates directly to physical control latency.
If the arm has to wait for a 13 billion parameter network to compute the next command, you get that serial bottleneck. It moves, pauses, evaluates, moves again.
And you can't catch a falling object or react to a fast environment like that. Which brings us to their deployment architecture. They split the problem. You have a high-level vision language model running slowly in the background at about 2 Hz.
Assessing the macro state of the scene.
Right, but it doesn't output natural language. It outputs a very rigid JSON schema.
It has a done signal, an instruction, a generation instruction for the expected motion, and a local scene description. And using JSON is so smart because unstructured text would waste the fast policy's compute cycles just trying to parse language.
Exactly. It gives strict parameters for the low-level policy to act on instantly. And that low-level policy is where the Foresight Reasoning inference loop comes in.
Which completely decouples the standard sequential cycle.
Right. Normally it's observe, process, act, wait for observation. But Foresight Reasoning is an asynchronous predict-then-correct loop. The model imagines future latents and predicts actions in parallel with the hardware actually executing the previous actions.
So what does this all mean? It's basically like a speed chess grandmaster. While the opponent is physically moving their piece, the grandmaster isn't just waiting. They're already calculating 3 moves ahead based on where they know the hand is going.
The neural network is drafting ahead of physical reality.
But that drafting introduces a big risk, doesn't it? Hallucinatory drift.
Yes. If the robot's gripper slips in the real world, but the network's imagined state thinks it successfully grabbed the object, it will keep generating actions for a reality that doesn't exist anymore.
Which is why the correct phase of that loop is so crucial. Every time a real observation comes in from the cameras, the model aggressively regrounds its key value cache.
It runs a learned for dynamics step and completely overwrites the stale, predicted context in the KV cache with reality.
Anchoring its imagination back to the real physical state.
Exactly. And to do this fast enough, they heavily optimize the acceleration pipeline. They use diffusion distillation on the flow matching ODE, which drops the sampling steps from like 5 or 10 down to just 2 steps.
And they use FP8 TensorRT quantization, plus they implement a flash infer paged and ragged KV cache, right?
Yeah, flash infer is huge here. Instead of treating the visual history as one massive block of memory that has to be reallocated, it pages the memory like an operating system.
Yeah.
The model only pulls the exact blocks it needs.
Which drastically cuts the VRAM overhead. And when you combine the Sparse MOE, the 2-step distillation, and the flash infer Lingbot VA 2.0 hits a peak asynchronous execution frequency of 225 Hz.
Which is just blistering for a 13 billion parameter model.
Fast enough that they actually validated it on incredibly demanding tasks like chip picking, grasping a thin, flat object off a table with 0 tactile sensors, Purely visual feedback.
And they even deployed it on an air hockey table.
Which is insane. Air hockey demands high-speed, purely reactive closed-loop control. You can't play air hockey with a serial bottleneck. The fact that it tracks the puck, predicts the physics, and strikes fast enough is the ultimate proof that Foresight Reasoning works.
It really is. It proves that bolting action modules onto generic video generators is over. Embodied AI needs native semantic tokenization. It needs causal temporal flow from day one and specialized asynchronous pipelines to decouple compute time from physical time.
It is a massive leap forward. Now, before we wrap up our deep dive today, there is one detail from their in-context learning pipeline I want to leave you with. To teach the robot how to adapt by watching a human prompt, they needed paired data sets of humans and robots doing the exact same task.
Which is horribly expensive and slow to gather physically.
Exactly. So they used a synthetic loop. They took real videos of robots performing tasks. They fed those into Gemini to get precise image editing prompts. Then they visually transformed the robot's grippers into human hands in the first frame.
And then fed that frame into generative video models like Wan and Kling.
Yes, to synthesize a temporally consistent video of a fake human doing the exact same task the robot originally did. We are using advanced generative AI to simulate humans completing robot tasks, just to teach physical robots how to understand human intent.
It is a completely recursive, closed-loop system.
Creating synthetic humans to train physical machines. So the question I want you to mull over today is this. As these models get better at generating their own physically grounded training data through pipelines exactly like this, where does the synthetic data loop actually end? Thanks for tuning in to AI Paper Slop. We'll catch you on the next deep dive.